Okay, the last thing that we did with this theorem that I'm clearly totally enamored with, that thing. And this is my favorite connection of valuation domains in reality. Then the integral closure of R is the intersection of B it's the intersection of all valuation over R, which is really cool that integrality can be expressed this way. And like I pointed out earlier, as a corollary to this, we went through some pains with this module theoretical stuff showing that the integral elements are closed under addition and multiplication. Well, this makes it immediate, right? Because once you have this theorem, then the collection of all integral elements are actually an intersection of a bunch of integral domains, so it has to be closed under addition and multiplication. So, let me give you a proposition. I mentioned this earlier, and I was actually kind of hoping that you all would pick it, but so I'm going to do it now anyway. Let me the evaluation domain. Then any over is also. This is a theme that actually shows up quite a bit in community algebra for certain types of domains, especially if they're nice. Once you hit that as an overring, then the rings above that, the overrings of it persist to have its property. So if you climb up any ring you want, the integers or polynomial or field, if you're climbing toward the quotient field, you're eventually going to hit the valuation domain. And once you hit that valuation domain, it remains valuation domain from then on. How would you prove this? It's actually super easy if you see the right thing. You might see how to show that W also has to be valuation domain. So, right. Let me fix this. Super mind. Take a non-zero element of quotient, right? It suffices to show that either that element or its inverse is in W, right? Well, if omega is in W, then W. If omega is not in W, then omega is not in V, right? Because W is bigger than V, so the sum W is not V. As V is the valuation domain, then omega inverse is in V. And so any element of its inverse has to be in there. So it's the valuation domain. That's kind of good to know. And let me give you a definition. I've tossed this word around, but you know, this is for completeness for your notes. Definition. What are the untitled domain such that each finitely generated ideal I and R primitive. Then R is called the basic. So this is just an ideal, or I'm sorry, a ring for a finite generated ideal as a principle. Let me make a remark. One, any PID Bayesian. Because every ideal there. What condition can I throw in? So PID implies Bayesian, the converse is not true, but it's an equivalent if and only a PID if and only Bayesian and a theory. So there are rings all over. There are examples of this. I'm going to give you a theorem. It's actually homework. And actually, I'm going to prove like kind of a little side junket on this one too. If an opening is positive. So an upshot of this is if you want a large collection of examples of Bayesian domains, all you have to do is look at valuation domains. And let me point out these are usually interesting examples in the sense that valuation domains are in a certain sense rarely there. Let me so if you wanted, so of course all the Bayesian domains that you get while looking at valuation domains are all quasi-local theorem. If you want an example of Bayesian domain, it's not a PID and it's not a valuation domain, then perhaps you might look at the ring of entire functions, the complex one. This is actually Bayesian domain. It's very strange properties. In fact, that one I believe is in dimension, as a matter of fact. So you can stack the primes as high as you want. Let me give let me do kind of a little side jumping before I actually go through telling you what in fact a valuation is. And you should tie this in together when I talk about valuation. So, if by theorem, a semi-local, or I'm sorry, quasi-local, PID is a value. And these are the only theory. And they exist in abundance, right? Let me give you some of these. These are all sort of different examples of the theory and valuation. See, localized it. Right, so all fractions from the rationals were not denominator growth to prime. Two, form power series over the field. Theory and valuation domains. Three. I guess so. Here. Suppose you have a integral domain that has a non-zero prime element. Yeah, that's not good enough. I need to take more. So there's no prime ideal. Such that zero. So this is sometimes called a minimal non-zero prime. So there's no, you can't squeeze any prime ideal down to zero. Then our localized P is I almost made a mistake and just said that. Anybody think an integral domain where this doesn't hold? Actually, I can give you a valuation domain which this doesn't hold, but it won't be in the theory. I'll give you that example in a moment. Four. So in particular, a good example of this is let R be a UFD, unique factorization domain, and let P be any non-zero prime. And that localization is the theory and valuation domain. The theory and valuation domains are just principal ideal domains only have one prime. And here's one for you, number theory, these ZP, yeah. We may talk about that later as well. These are all examples of the theory and valuation domains. And what they all have in common is if you have a theory and valuation domain. P. And then prime ideal is generated by P, there's 0. That's the Maxwell ideal that's generated by P. In this case, the role of P is played by P. The role of P here is played by X. The role of P here in our low plus P is played by P. And in the P added integers, it's also P. And here's what the ideals look like. It's totally non-test. That's it, right? It's just the powers of P and flats and everything. Right, so ideal theoretically very important. All of the theory and valuation domains in a certain sense look like this. But the examples that I've given you are not isomorphic. Z localized P and P addicts, power series, these are usually not isomorphic rings. However, their ideal structure is the same. They have this unique Maxwell ideal generated by the principal P and collapses down. Okay. But I did say that most valuation domains are not. Let me build you a one-dimensional, non-dimensional. I'm not going to dwell too much on the details. I just want to feel about abilities. Anybody know how to build, right? So let me point out that every theory and valuation domain that I built, and all of them actually are one dimensional. And what do I mean by that? Well, the ones I built here are one dimensional, and that means that 0 is a prime ideal, and then there's a Maxwell ideal generated by that prime element, and that's it. That's a Maxwell ideal. I have glossed over a trivial case. You could have 0 being the Maxwell ideal and that valuation domain being the field, but I'm going to ignore that because that's silly. Right? Can anybody think of a one-dimensional valuation domain? So you've got 0 and then you got the Maxwell ideal, but now the Maxwell ideal is not principal. In fact, it won't be finite generated. How would one build such a? That's kind of weird, right? I mean, 0, and then you've got just one idea. I'm going to build this in stages. So start with the following group ring. I'll see. Pick your favorite field. I don't care what it is actually. These are non-negative fractions. Okay, so what in the blue places do I mean by this? This is sort of generalization of polynomial, right? Where do your exponents come from in a polynomial? Can your exponent in a polynomial be, I don't know, I or -3? No, the exponents actually come from the natural number, right? So what are the acceptable exponents for your variable x when you're in a polynomial ring? Well, 0 and 1, 2, 3, etc. like that. Notice that that set of elements forms a monoid. Actually, I should call this a monoid. It's commonly called symmetry. And why do you need that? Because x to the a, what's x to the a times x to the b? It's x to the a plus b. So you need your exponents to be closed under addition. Otherwise, you run into trouble, right? You fall off the end of the world if a plus b is no longer in your acceptable list of exponents, right? Well, it's easy to see how to generalize that, right? Because with an ordinary polynomial ring, I let my exponents be natural numbers. Well, why stop there after all? How about letting them be positive rational numbers or even real numbers if I want to go really bananas, right? So why not, right? So a typical element of this looks like alpha I x to the q sub I, where alpha I is in field, and q sub I is in q plus, and my q plus includes C. Right? And what happens when you multiply x to the q1 times x to the q2, get x to the q1 plus q2 is still a positive radical, so I'm feeling all warm and fuzzy inside. Right? So this actually forms an integral domain. Right? And you can almost use degree type arguments because in fact everything's a finite sum, right? And so if I walked up to you and I said, okay, and let's take let's actually for this can be any field, but for this computation, because I'm a lazy man, let's just take F2 because then I've just got zeros and ones, right? I gotta love that. So what does a typical element look like here? Well, it's a polynomial that has exponents from positive rationals, right? And it's got either 0 or 1 as a coefficient. So basically, here's what things can look like. They can look like 0. Well, in fact, let me try this way. Epsilon 0 plus epsilon 1 x q1 plus epsilon 2 x q2 epsilon x q1. Where epsilon I is 0 or 1 and qi is -. Now, what I'm going to do actually is I'm going to make my valuation domain here. I'm going to let it be this localization. Actually, that makes sense, right? Because valuation domain is supposed to be quasi-local. So where M is the ideal generated by x to the q such that q is bigger than 0. Right? So if you look at an element of this is in the Maxwell ideal if and only if epsilon 0 is equal. Right? Because if epsilon 0 is 0, that means that everything has a positive, every term in that is a positive power of x, and so is in the Maxwell ideal. And if epsilon is not 0, 0 is not 0, then element is unit when localized. Because remember, if that's a 1, then that means that's in the multiplicative with both set of elements start with 1. And so it's in my set of denominators. So locally it turns into a unit, right? So I can kind of forget about it. So let me show you what elements of this valuation domain look like for a typical element. So if I were to classify the elements, one kind of element that is 0 itself, certainly 0 is there. For number 2, a unit, right? Not to use unit. For number 2, something that's in that Maxwell ideal in MR of M, and even though that can be a fraction, I can just multiply it out. I can multiply it by whatever the denominator is, and equivalent up to the unit, polynomial in the original ring, something in the form xq1 plus xq2 plus xqn, where q1 plus q2. Right? So actually, The third type that's not a unit can still be written as a fraction of something over, oh no, it starts with 1. So basically I can multiply it by that denominator, and that's equivalent to something that looks like that. Right, okay? Now check this out, which is kind of cool. This is actually x to the q1 times 1 plus x to the q2 minus q1 plus x to the qn minus q1. Agreed? And that bad boy is a unit. All right. So here's what happens in this valuation. Given two non-zero elements, they look like this. U1 x to the Q1, or U2 x to Q2, where U1, U2 are units in the valuation domain, and Q1, Q2 are greater than or equal to 0. If it's equal to 0, then of course that means that it's just a pure unit. One of these has to divide the other, because just look at Q1 and Q2. They're just two non-negative rational numbers. One of them is smaller than the other, or equal to, and that one is divided. So this is valuation domain. However, let me give you a quick proof that the Maxwell ideal of this is not finitely generated. Since every element in V is basically a power of X up to a unit, and since this is a Maxwell ideal and I can't have any units in there, then the Maxwell ideal, if it's finitely generated, must be this. We'll say with Q1 less than Q2 less than Q1. Everybody agree? Note X Q1 divided by 2 is not in, so that Maxwell ideal can't be generated. So this is a great example of, oh, by the way, I guess I did also put this one dimension. So here's what we have so far. In V, we have the 0 ideal, and then we have this M, which is actually generated by X to the QI, or X to the Q, say, Q to the 0. Can anybody explain why I know that there is no prime ideal that sits properly in between there? So M is our Maxwell ideal. It's very natural to ask, hey, why can't there be a smaller?
Not generated by everything. Then you've got something not in there until multiply.
Okay. And in fact, this idea was really kind of slick. It's not finitely generated, but it's radical of principle. In fact, this is the radical of every non-zero idea. So, for example, so suppose always suppose you have a non-zero prime ideal. Between there, I claim the Q is all of them. Right. Well, since this is a non-zero prime ideal, where is this? Now, let X to the Q be any element that you want, right? Now, what we're trying to do is show that Q and M are different, right? Right, so let's suppose that there's something in Q on there. Anybody see how we're gonna get this solved? It's a pretty radical approach. So let's do this, all right? Probably the best way to go about it. So, right, well, let me do it. I'm gonna do 2 things. If Q is greater than or equal to beta, then X to the Q, then we'll say that Q minus beta is greater than or equal to 0, right? So X to the beta times X to the Q minus beta equals X to the Q, and this of course is in V because Q minus beta is greater than 0, and this is in X to beta. So it must be the case Q is less than beta, right? But the rational numbers, in particular, the real numbers, have the Archimedean property. Yeah, are you all familiar? So I feel like I'm kind of off course again. So what this means is, since Q is strictly greater than 0, I can actually find the natural number that's big enough to multiply N by Q and exceed beta. Right? So therefore, X to the Q N power equals X to the Q N, which is N, because this is bigger than beta. This is so what does this mean? So X to the Q is N, X to the Q N, Q, and Q is prime. So X to the Q, and in fact, corollary terms again is that Maxwell ideal is the only non-zero prime ideal, and it's radical of every non-zero ideal. So there we go. You've got 2 kinds of one-dimensional valuation domains. Ones that sort of look like this, and this can be a little fuzzy because actually notice that your exponents come from the rationals, but I can actually have my exponents come from any totally one field group. Well, positive part of it. for example, real numbers. Or you have what we call sometimes a theory evaluation domain called discrete, because basically the powers there are just integers, right? The squared. How about bigger evaluation? Right, this is two stack column. Here's another example. So again, I'm going to start off this way. Now, what's going on here is this is just an ordinary polynomial ring over a field, so in two variables. And again, if I do computations here, I'll build two elements, although it doesn't matter. And what I've done is I've also thrown in these other rational functions, y over x, y over x squared. And so the result is, actually, one of the interesting things about this is notice that when in this ring here, y is kind of weird because it is divisible by x arbitrarily large number of times, right? Because this times x squared is this, and this times x cubed is this. And so you've got arbitrarily large number of factors of x, right? No unique factorizations here. This is a weird domain. And here, what I'm going to do is I'm going to let M be the Maxwell ideal generated by all these rational functions. Now I'm going to play a little bit fast and loose here. I'm going to be a little bit less than precise. Kind of give you an idea of how to do this. When you localize here, like a typical element, you can think of as a polynomial in these variables, right? So it's sums of products of things here. Notice this times this goes back to this and so forth. You can take powers of this, multiply it any way you like. If you have a non-zero constant, then it's a unit, right? The Maxwell ideals are ones that, if you think of this sort of loosely polynomials, if you plug in 0 for y, and then after that plug in 0 for x, if you get 0, that's in the Maxwell, right? Otherwise, it's not. So what does a typical element look like here? Well, so let me kind of take this apart, like maybe a little bit less. I mean, I can do this in a much more streamlined way, but I want us to kind of see computation that's going on. If you have something like, x plus x cubed, x to the 6, something like this. Notice you can pull out the lower power of x you see, and this is really x times a unit, right? Because this thing is outside the max quantity. I guess you could do this with a polynomial purely in y as well, couldn't you? The real question is what happens if you mix x's and y's? Let's start off with something simple. Okay, well, this is kind of boring because I can pull an x out, right? Well, what if I couldn't, right? Ooh. Oh, horror. I can't pull an x out anymore. Or can I? Right? That's a 1, no problem up there. X, y. And it looks like there ain't no x in there, but boy, there's a lot of, right? Because really, in fact, y is divisible by x, so certainly so is y cubed. And this is a unit. Huh, how about them apples? Now, what if I have something like this? No, I guess. Let me do it this way first. So let me ask you this. I have a 17 here. What can I pull out of this? I can certainly pull Y out, right? Because Y squared is also going to pull out the parallel I want, and I get X6 Y4 plus X17. Now what? Right, I can pull that X17 out too, can I? Right? So this would be Y squared over X to the 21 plus X6 over Y4 over X to 11. And this is a unit. So this is actually a unit Y X17. Let me change this a little bit. What if it was like this? Y2 over X4 plus X7 Y5 plus Y over X squared. Well, now I can't pull that Y out anymore, right? Because that would leave me with a -1 over X squared, which is a no-no. But undaunted as I am, why don't I just pull out the whole thing, right? This is Y over X squared times, this leaves me with Y squared over X squared, doesn't it? Plus Y4 X to the 5 I'm sorry, X to the 9 and plus 1 again unit. So the upshot is any element. So here are the types of elements. You got 0, which is kind of a degenerate by itself case. You have this type of element. By the way, up to units, right? So you can have X to the N times the unit. N greater than or equal to 0. Naked X's always have to appear with non-negative powers. If they're coupled with Y, though, here, U a unit A greater than or equal to 1 in any unit. Now, let's do the Pepsi challenge on this stuff, right? So I claim that this is valuation domain. I claim any pair of elements can be compared, any pair of non-zero elements, right? So one. I can certainly compare those, whichever is the bigger n, whichever is the smaller divides. Two. By the way, I know which one divides the other one this time. Which one divides it? The x to the n divides it, right? Because I allow any power of x to appear when I've got at least one y. And actually, I should have said y with k here. K greater than or equal to 1. And n greater than or equal to 0. There we go. Any power. So, and what happens finally? What if you compare things like this? Y to the k1, x to the m1, u1, and y to the k2, x to the m2, u2. Where k1, k2, greater than or equal to 1, m1, m2, greater than or equal to 0, and u1, u2 are units. How do we fight this battle? So which one divides? What's the algorithm?
One of your K's is strictly larger.
Okay, so let's suppose one, if K1 is strictly less than K2, then what happens?
The first
Right, because you're gonna have some positive Y's left over if it's strictly less. And then, so you'll have some positive Y's left over, and it doesn't matter what you do with the X. Then and what about what if they tie? That's the only thing left, because what if you get a tie on the Y? What happens? It's like it's like looking for a book in the library, right? I mean, if you've got, oh, I've got 2 books I'm looking for, they start with a D, right? Well, then you go to the next letter, right? And that's exactly what happens. If you win here, then you can sort of think about dividing these out, and now you run the contest. Yeah. And notice you can compare any 2 non-zero elements. Let me point out that you can build this valuation domain. So here's what the prime spectrum looks like here. In this one, the Maxwell ideal, actually M is principal, because X is the element, X to the first power divides everything in that ring. Oh, everything in the Maxwell ideal, I should say. So X is the principal ideal. This thing with all the crazy Y's in it, that's our height 1 prime, and then we got 0. Right? So this is a 2-dimensional valuation. Notice that 2/3 of those ideals are in fact finally generated. All it takes is that 1 prime in the middle for everything off. And guess what? There is no end to the fun, because you can go crazy with it. You can do this. There's many variables. If you want to localize and build all these different crazy ones, you can build valuation domains that are so big that they have a Maxwell ideal, but they have no height 1 prime. So you have 0, any prime ideal you have, you can always squeeze another one in there, right? And you can build these things crazy here. So anyway, any questions on that? Let me say also, if we have somebody coming in for the math club day, she's coming all the way from Kentucky in this rain. So it'd be great to see her. There's lots of stuff about data science in there. And most of you probably have more of an interest in algebra, but I think it might expand your horizons a little bit to, you know, the whole marketability thing, to give it a shot. So come by if you get the chance. Otherwise, y'all stay dry and have a good weekend.
That, so you're saying, that feels like dark, 3-dimensional.